Thanks for sticking around, looking at the weather. Maybe some of you said, well, I have no place else to go, so I may as well stick around. I think I was presenting at pretty much the last session in Brussels, and it was also, again, a lot of people saying, well, I'm going to catch the flight out in the afternoon. So thanks for coming. For those of you who were in Brussels, anybody here in Brussels? A few people, right? So I used the same system again, only this time we went with Spark Machine Learning, and again, try to take it through its paces. So the thought is, how are we using Spark ML? And there's, as if I could speak for all the different ways IBM was using Spark and Spark ML. So this is a particular slice that I'm going to talk about. Tell you a little bit about the experimental environment. The hardware is the same as for the Spark SQL tests that we ran last year. The workload's a little different, so I'll go a little bit into that. And then, we looked at how we could study the scalability of Spark ML 2.1 in this large cluster environment, present some initial results, some surprises, some things as we expected. And then, as you might imagine, since 2.1 just came out at the end of December, lots of future work for us to continue on with. So the context is, you've heard at this conference as well, multiple companies talking about the desire to democratize data science, how to make it available to everyone. Part of that is making it so that, the many people out there who are not as skilled at data science as the people in this room, how can we help make it easier for them? So IBM's launched something called Data Science Experience, which brings together, tutorials. It brings together an environment for, data wrangling and machine learning, and allows you to explore that space in a collaborative environment. And within that, there's a segment that's focused on machine learning. And in that, and as we've seen multiple pictures very similar to this, there's this feedback loop of machine learning workflow, and I won't be covering all of it. That could be a whole talk on itself, but most of you are pretty familiar with this at this point. So, we wanted to study something that would make use of a big cluster, and so we thought a good place to start is model training. Another thing I'd like to do is do something really high-end with model scoring, evaluation, but for that you sort of need lots of a big front end as well, and this was just a single back-end cluster, so we focused on the model training. So that's really the emphasis of this particular talk. And so, the piece of that is called Watson Machine Learning. For those of you who were in the expo, there was a chance for you to see that. I think it closes in a few minutes, so I guess if I see mass exodus and everybody is so excited by what I've just said that you're going to run out the door. But this is something that we're just in the process of launching that essentially automates a large chunk of this overall workflow. Now, the things that within the machine learning workflow, the model training we wanted to study is, if you have the opportunity to use a whole variety of machine learning algorithms, which one should I choose? And for many of you, that's probably an obvious decision, but for lots of people who are just getting into this, it's not so obvious at all. They have funny names, and people write competing papers about which one is good, and it depends on lots of factors, and so it's a little bit tricky. And then even if you are clever enough to choose one of the better algorithms, they have an increasing number of hyperparameters, and they're pretty cryptic as well. I know a bunch of them I was not familiar with, and it took me a while to even get to people who really knew what they were doing to explain to me what all these hyperparameters were all about. And so if you imagine the combination of all the algorithms and all the parameters and the values, it's a pretty large space. So you could spend a very long time, both people time and human and machine time, exploring that space. So what we've done is leverage some research in IBM. It's called the Cognitive Assistance for Data Science, which tries to intelligently help you in an automated way explore that space. And so we use that new research algorithm embedded within the Watson Machine Learning in order to conduct these experiments. So I've chosen a couple of slides here from a research presentation that just gives you the tiniest overview of what this does. So you've got a problem, and there's this controller that says, hey, I'm going to try all the algorithms I think are appropriate, try them with a little bit of data, see what the results are, score that, and the worst ones, discard them, and the ones that are still in the running, kind of like a runoff, we try them again with more data, and we repeat that process, iterate over some number of iterations until we have a winner. And then we can learn from that, and you can combine this both algorithm selection as well as hyperparameter selection. So that's kind of the idea. There's some math behind this that I'm not going to go into. There's a nice, in the bottom left corner, there's a nice research paper that you can read that tells you all about this. It's called data allocation using upper bounds. And the basic idea is you tend to rely on the fact that these algorithms have sort of a nice regular shape, kind of a curve, and by doing that even you expect that them not to be kind of really squiggly in terms of how they behave as you increase the amount of data that you use to train. And so, of course, you can, each of these iterations will run with some degree of parallelism, but you can also run all these experiments in parallel as well. And by doing that, if you have lots of computation power, you can actually dramatically reduce the overall sequence or time it takes to run through all the combinations that you are willing to use. And I'd say most of us as humans, we tend to go through these fairly sequentially, and at some point we just say, you know what, I've got a deadline to meet, my boss has told me I have to have this thing running by Friday, and good enough. And they don't really know how much opportunity they're leaving on the table. So this is in trying to do a very intelligent way of kind of navigating the possible space, using some heuristics, but also using a feedback loop of data that actually evaluates how well it's doing on some amount of data. So that's kind of one of the key algorithms that's embedded inside the Watson machine learning within the overall data science experience. So I'm going to very briefly review the cluster. Again, this is the exact same cluster that we used for the 100 terabyte Spark SQL results that I presented in Brussels. It's for those of you who are not there, it's a sizable cluster of, I would say, slightly non-typical or atypical Hadoop nodes in the sense that they tend to have more cores and more memory than what a classic Hadoop environment would have. But it is one that I think is much more appropriate for the world of Spark. It's very rich in memory, and it uses NVMe SSD drives. So and it uses 100 gigabit Ethernet. So we've done sort of everything we could to make this be a high-end, high-performance, as bottleneck-free as possible, or to move the bottlenecks as far as we can. We call it F1. It's, our internal name was a Formula 1, but that's a trademark name, so I can't put that in the slides. And the idea is it's sort of, if budget is not really a consideration, then here you could put a very fancy cluster together. And we did this jointly together with Mellanox and Intel and Lenovo. So it was sort of the four companies that got together and spec'd out this cluster and put it together. And the idea is that we're going to sort of understand where are the optimal spaces in terms of this from a more practical commercial environment. And as a result, we hope to come out with kind of a reference architecture that uses these components, but maybe does a little bit of cost optimization. So, for example, one of the tests that we're just in the middle of right now is for both Spark SQL as well as for machine learning. If we don't want, to use the highest density DIMMs all the way up to 1.5 terabytes, what happens if we go with 1 terabyte or 3/4 of a terabyte or 0.5 terabyte? What's the ratio of the price curve versus the performance curve to find that optimal point? So it's a really fun cluster to play on. So I like these kinds of toys. All right, so there's lots of gory details. So I mean, in the last talk, people were asking, well, what are the specs? So there's all the specs. I won't go into it. To me, at the bottom is, you've got over 1,000 cores, over 42 terabytes of RAM, and over 440 terabytes of fast NVMe SSD. So hopefully you'll all agree that's a sizable cluster with which you can experiment. And one of the things we learned with Spark 2.0 with Spark SQL was that as we increased the number of nodes, things actually scaled relatively well. And one of the hypotheses we wanted to test is if we do this with Spark ML algorithms, do we get the same kind of behavior? Now, for the Spark SQL tests, we used the TPCDS environment and data generation, which is what lots of people in the world of SQL have been using. So we thought, well, what should we use for the machine learning? And TPCDS is not so ideal for that perspective from a number of perspectives. And so we did a bit of researching on what do other people use, and it's a real potpourri of things out there. Now, it turns out that I knew a professor in Barcelona who had founded something called the Linked Database Benchmark Council, and they had done some interesting work for graph databases. And I wanted to see if we could adapt their artifacts for machine learning. And so within the LDBC, they defined a couple of benchmarks, one of which is called the social network benchmark. And the thought I had was, gee, if a social network is trying to represent in a graph form what people are doing, what do people like, how are they connected with other people, all these relationships, then there might be some data there from which we could learn patterns in order to make recommendations or predictions and so on, typical machine learning types of activities. So that's what we've chosen. So again, for those of you who've never heard of the LDBC, and if you're curious how to maybe try this yourselves, there's a bunch of information about where to find them. So for those of you who know the TPC, it's kind of modeled on that. They have a website. It's all free. It has a nice Apache license, so you can get the source, you can modify it very freely. It is synthetic data, and we had lots of debates internally within IBM. Does it really make any sense to use synthetic data for machine learning? And so we'll come back to that. So the benchmark itself consists of all the typical pieces of a benchmark, and we only use the data generator for this particular part. The rest, for now at least, we've left aside, and we've only really begun to explore this space. But I wanted to introduce you to this because I think lots of people are looking for ways of exploring things with synthetic data or with benchmarks so they can experiment without having to worry about privacy and things like that. There's a picture of the high-level schema. So it's a reasonably complicated one, and in a particular aspect that we focused on for this particular experiment was this relationship between a person and topic classes and topics. And so some person has an interest in a topic, and that's biased by what country they're in. And if they're from a country, then their likelihood of them being interested in certain other subtopics, is higher than from another country. And so there's some non-uniformity, there's some correlation, all kinds of properties that one could sort of detect. And of course, we had the source, so if we wanted to salt the data with a pattern that we would then get machine learning to detect, that's something we could do. So the focus then for our experiment was we wanted to understand for a prediction system, for different algorithms that you're trying to choose which is the best one. Well, if you run this on your laptop, it could take a very long time before it comes up with that answer. So we wanted to see, can we scale that out over this big cluster and get the answer faster? And then similar to look at another aspect of things for a recommendation system where we've picked the algorithm, but it has a bunch of hyperparameters. How quickly can we explore the space of hyperparameters? And again, we're using the Watson machine learning with this cognitive automation of data science. So I've already explained there's this has interest, attribute, and so we wanted to say, if a person is known to be interested in one topic, can I predict the likelihood that they're interested in other topics? And we chose these set of algorithms. I'm sure it's not complete. It's probably not even the best one. I don't claim to be a data science expert at all, but these are ones that are all in Spark ML, so that seemed like a good starting point. And then we wanted to see how well that scaled. So first we had to do the data preparation and make sure nobody gets misled. We started off with a very large, from the perspective of a graph database data set, but by the time we extracted all the elements, we got down, you can see in this particular case, down to 30 gigabytes of file data that represented the actual important data. So it wasn't, while we started with 100 terabytes, the actual amount of data we were working on turned out to be pretty small. And I think that from speaking with clients, that's actually very common that you start off with a lot of data, but when you get ready to run your algorithms, it's you shrink it down a lot. So for 30 gig, I'd say 1,000 cores is probably a little bit of overkill. And so one of the things we did is we, for the purposes of both meeting the deadlines for this conference, and since you'll see in a moment the scalability was less than perfect, we only used half the cluster for all the experiments. But it was still 14 nodes, each with 36 cores. So it's not exactly like we were keeping the system underpowered. All right, so here's the first set of results. As we moved from 1 to 14 nodes, we thought, well, add more nodes, you should go faster. Now you can see the tuning parameters for Spark on the right side. A lot of these were derived from our results from Spark SQL. What I mean by that is that we have, in fact, a pretty regular set of parameters, and as you add nodes, you just keep adding more executors, but you keep all the other ratios fixed. And since we had lots of memory, it all worked very well. So the first pleasant surprise was, in fact, that Spark 2.1 really ran stably. So in all these experiments, we never had a crash, and we'd learned enough from the Spark SQL testing that we didn't run out of memory, and so everything behaved nicely. So that was actually very positive. Now, for those of us who care about scaling, we didn't really like the shape of this curve after 4 nodes, right? That wasn't really what we were hoping to see. And so we said, okay, well, we've at least learned that up to 4 nodes looks pretty good. Not perfect, but pretty good. Let's stick with that and see what else we can do. But of course, it was nagging us, and I presented these results earlier this week to our Spark Technology Center Advisory Council, and immediately got the question, well, why does it behave like that? And it could have been any number of things, right? Could have been Spark, could have been the way we tuned it. It could be the fact this Watson machine learning CADS algorithm was misbehaving. Could be any number of things. And so one extra test we managed to run just since Monday is we said, well, what happens if we fix the number of executors, but we keep scaling more nodes? And to our delight, I guess I could say, we got some more benefits. Still not great scaling, but it certainly improved. And so we looked at some of the profiling data, and it seems like we are with so many nodes, we've got a lot of coordination going on. The scheduler's pretty busy. So it looks like we might be finding some kind of bottleneck there. So there's more work to be done to get to the bottom of this. But that's the result so far, is that it looks like when you're running machine learning that just throwing more and more executors at it may not be the optimal answer. Right. So now remember that one of the things CADS can do is it can run lots of things in parallel. And so just to understand how well that worked, we kind of forced it to just run one at a time. So you can sort of see the stacked bar chart where it tried each of the 6 algorithms individually. You can see that some took longer than others. But if you compare that with using the Watson machine learning approach with CADS, where it tries to cleverly combine things, it did pretty well. So you had lots of CPU, it made good use of that CPU, and shortened the time to come up with a recommendation. So that was the prediction system. And then we tried the recommendation algorithm. So here we didn't try different algorithms. We just said, let's pick alternating least squares, and let's focus on hyperparameters. And we chose 3, and they have lots more possible values than the ones that are listed here. But with some of them, we were finding, for example, rank, that if we increased that number, the run times were really shooting up pretty substantially. And so again, keeping an eye on the time and how many days or hours we had until today, we decided to prune the number of combinations. So we tried all the combinations of these to see what would happen. And again, we had to do some data preparation. In this case, again, in the interest of time, we decided not to use the 100 terabyte data set. We shrank it down to the 3 terabyte set. And to me, again, this is one of the nice things about using synthetic data, is that you can very quickly vary the amount of data that you're using. You don't have to worry about copying files from all over the place. And so what we did there is, we basically came up with, a nice little simple idea, keeping track of people and their interests in a particular topic. And we wanted then to be able to try all these different hyperparameters and, again, vary the cluster size. And so here, interestingly enough, we got, I'd say a nicer curve. We didn't see that rise again as we went beyond 4. Still not, great scaling. If this was in the world of SQL database tuning, this would not be a stellar scaling result. So that was the first result we had. The other thing, of course, is we wanted to sort of see this CADS algorithm in action. So here you can sort of see all the different algorithms going through different iterations, and what happened at each one, you can sort of see the root mean squared error, keeping track of how well the algorithm is doing. And so you can sort of see that as with each iteration, you're using a greater percentage of the training data. So we kept, some of the data aside for validation and test. This is just the training set. We used a 60% split for training. And you can sort of see with each iteration, we tuned CADS so that it would double the amount of training data it would use until, of course, once you get to 80%, you double that, you get to all the training data. So you can see, so for some of the algorithms, they kind of relatively quickly, they're not improving much, they're behind, and then they get discarded. And then CADS goes on and tries to actually focus in on the remaining algorithms, give them more data, and so on. Now, one of the things that we observed is that there's actually more algorithms than you can see colors, and that's because they're really sitting right on top of each other. So you'd have to really scrutinize it more closely. And so I think we have more work to do where we didn't have, I'd say, enough interesting data in the synthetic data in order to really sort of tease out the full attributes of this. So I'd say that our idea of using synthetic data was only a partial success here. We were really actually a little bit, it was too easy, right? So the algorithms too quickly, and they all got the same answer, and it was hard to discriminate between the strength of different algorithms. I've talked to a few data scientists, and they've sort of said, well, sometimes that happens on real data too. So it's not a totally unpredicted result. And for many people, if this actually obviates the needs to do lots of heavy lifting and lots of human time to figure this out, it might still be a good enough answer to proceed with a project, saying you're getting a pretty good answer and you have a pretty quick vehicle for getting to a pretty good algorithm, which lets you get on with your job and move on to something else. So that's what we've achieved so far. We have lots more to do. We definitely want to try it with more algorithms. We definitely, we've only explored one very narrow piece of this social network benchmark. We want to still learn more about all the tuning parameters of Spark in order to make things run better. One of the things overall that I think are still challenging, and a few people have remarked about this at this conference, is that it's not always easy to know, how to set the Spark tuning parameters. In fact, there was a Q&A session this morning where somebody asked that question, and the answer was, well, if you're just starting out and you don't know how to tune Spark, then expect to spend some time learning how to tune Spark. So I think was sort of is my restatement of the answer that was given. And so there are some embryonic capabilities in Spark to do this dynamic resource allocation. We gave them a quick try and had sort of total failure, and we didn't have time to explore it further. But my sense is that those automatic tuning options are still embryonic and need more community support and maturation before they can be used in production. Obviously, there's more attributes of the Watson machine learning we want to explore. It's going to be able to do automatic feature selection. That should be interesting. Also, the model evolution with the feedback loop is going to be very interesting. I already mentioned at the beginning of this talk that we want to be able to do the scoring performance as well. And that should be interesting because, just like with the streaming where people talk about latency, I think with scoring there will also be some latency concerns if you're trying to actually use Spark for the scoring. I mean, other people I've talked to have told me, well, once you've got it all figured out, for the actual scoring, you sort of recode the solution in a non-Spark way so you can do super fast scoring, and that's something I'd like to actually avoid. And then lastly, we want to continue to track the evolution of Spark. In the course of just the last month, there's a number of JIRAs that we've uncovered for which we think that if there are solutions delivered, we think they will make the overall environment much nicer for us. And with that, quick summary, we've certainly proven that you can, even a big cluster, you can keep busy for hours. So if you think of how many core hours that is, that's an impressive amount. I'm glad I'm not paying by the minute for that one. Watson machine learning seems like a promising approach in order to automate this and use sort of intelligent algorithms coupled with lots of resources to kind of grind through some of this pretty quickly in order to give you a pretty good answer with a very modest amount of human intervention. This large cluster, we weren't able to fully exploit it yet, I'll add, but it certainly helped us a bunch. And as I said, there's lots more work to be done. With that, more or less on time, if you want to try it out, there's a website where you can sign up, so as soon as the beta is released, you can get on there and try it out yourself. So I'm happy to take some questions now.
Let's give it a hand.
Hi, great talks. I have a general question on the what's machine learning, especially the methodology used in the CAS, especially the methodology used in the CAS system, right? So the methodology essentially is you have a bunch of algorithms through a small kind of representative data set at each, and kind of pruning out some of the less promising algorithm up front, and then you focus on the kind of the early winners, and you kind of do exploring their tuning and hyperparameter selections, right? So my question is that in your experience, in your group's experience, have you had cases where anomaly happens, meaning that these early losers, right, that it could actually be the eventual winner if they have gone all the way to the full data set and also the full exploration for all their hyperparameters.
Right.
So, thank you.
So great question, and I can definitively say that in the 1 month of experience with this, we haven't encountered that. But it's just like proving in testing. I didn't find a bug for a month. Does that prove that the bug doesn't exist? Absolutely not. So I don't think I would in any way claim that I have explored this space long enough, thoroughly enough, to be able to make sort of definitive claim. I will say that Horst from the IBM research team, he's put a lot of work into this over a number of years, published a number of papers. There is some good math behind this, so it wasn't just a random thought. So I'd say even if you go read the paper, you'll get a better understanding of the mathematical foundation behind his approach. I would say it's probably not provably absolutely correct. Like many things, it's sort of a probabilistic approach. So is there a scenario where you could imagine such a scenario happening where more data suddenly takes a loser and turns into a winner? I think it is. And I think a lot of it depends on the core properties of the algorithm, right? If they're nice and sort of convex curves and they're nicely behaved, then I think that's unlikely. But there are classes of algorithms that take more of a randomized approach. I suspect those would not have those properties and would be far more likely to suffer from us thinking they're bad when they're really good. Okay?
Hi, Berni. This is Ravi Kaushik from American Express. I like the way you've designed the benchmarks with regard to classifying how to look at the algorithms. Wanted to understand the data. Have you looked at different kinds of data, like unbalanced versus balanced, that you may think of the algorithms may perform very differently, and along with the Gini and maybe capture rates?
Right. So what we knew we didn't want sort of classic TPCC style perfectly uniform data. So we actually sought out a data generator that had inherent properties of non-uniformity and correlation and things that are all attributes that we've learned from the world of relational databases are attributes that are absolutely present in real life data, like at American Express. Right? You have some card-holding members that shop a lot more than others and things like that. And they shop more in certain parts of the world than in others and so on. So there's lots of things like that. And there actually is a nice Sigmod paper about the social network benchmark data generator, and they actually used real live data from Wikipedia and other things to try to inject an element of realism into the data generation. And so we, on that basis, kind of trust but verify, we went with this one. I'd say that preliminary results show that it's still not messy enough. And in fact, one of the other things that I think is missing is that it needs to have some bad data. because real data always has bad data, and this is not. We need synthetic bad data too. So I think we're going to need to evolve the data generator. I still think it's going to give us a big initial boost, but there's more to be done to make it a better representation of the real world.
Awesome. And with that, we'll be taking a break. I think it's break time now. And then, circle back in 30 minutes or so. But let's give Berni another hand. That was awesome. Thanks.
Thank you.